Have you ever wondered why a hot cup of coffee cools down or why a metal spoon gets hot when left in a bowl of soup? Well, the answer lies in heat transfer. Hello and welcome to my YouTube channel. This is Alexa Elsabate, an agricultural and biosystems engineering student. And in today's video, we will be tackling about the combined conduction and convection heat transfer. So what are we waiting for? Let's delve in. Good day, future engineers! Today we'll be tackling about the combined conduction and convection heat transfer. So first, let me introduce to you what is conduction and convection in heat transfer. Conduction is the transfer of thermal or electrical energy through direct contact. Heat naturally moves from areas of higher temperature to lower temperature as vibrating molecules collide and pass kinetic energy along, and it occurs most effectively in solids. While convection is the transfer of heat through the physical movement of a fluid or liquid or gas. When a fluid is heated, it expands, becomes less dense, and rises. Cooler, denser fluid then sinks to replace it, creating a continuous loop called a convection current. So how do they combine? Heat transfer is not a choice between conduction or convection. It is a continuous chain reaction, meaning conduction and convection work together. As one process ends, the other begins. Heat first travels through a solid via conduction, reaches the surface, and it's immediately swept away into the moving fluid via convection. It means that heat moves through the solid first, then the moving fluid carries that heat away from the surface. Energy must be conserved. The heat leaving the solid by conduction must equal the heat entering and leaving the fluid by convection, meaning heat is not created or lost. The heat leaving the solid is the same heat transferred to the fluid. Now that we understand how they work together, the next question is, where does the combination of conduction and convection happen? Even in a fast-flowing fluid, the fluid molecules directly touching the solid surface are completely stationary, or known as the no-slip condition, meaning at first you might think all the fluid is moving. However, the fluid molecules touching the solid surface actually remain still. And because this thin boundary layer of fluid isn't moving, heat cannot convect through it. Instead, heat must conduct through this microscopic stagnant fluid layer first, before the moving bulk fluid can carry it away via convection. Meaning, since this very thin layer of boundary layer is not moving, convection cannot occur there. Heat must first pass through this stationary layer by conduction. Once the heat reaches the moving fluid beyond the boundary layer, it is then carried away by convection. This is why conduction and convection always work together at a solid fluid surface. To solve combined heat transfer, engineers treat heat flow like an electric current, temperature difference like voltage, materials like resistors. Heat does not transfer from one fluid to another all at once. Instead, it passes through three thermal resistors connected in series, just like electrical resistors. First, heat moves from the hot fluid to the wall surface by convection. The resistance to this process is called the first convective resistance. So the formula is the first convective resistance is equal to 1 divided by H sub 1 then times A, where H1 is the convection heat transfer coefficient of the hot fluid and A is the surface area. And take note that a larger H1 or larger area means less resistance, allowing heat to transfer more easily. Second, heat transferred through the solid wall by conduction. This is called the conductive resistance, and the formula for this is the conductive resistance is equal to the wall thickness, or the L, divided by the thermal conductivity, or the K, and times the area. And note that a thicker wall increases resistance, while a material with high thermal conductivity, such as copper or aluminum, decreases resistance. For the third one, after passing through the wall, heat enters the second fluid by convection. The resistance is called second convective resistance, and the formula for the second convective resistance is equal to 1 divided by H sub 2 times A, where H2 is the convection heat transfer coefficient of the second fluid, and the A is the area. And again, a higher H2 means lower resistance and better heat transfer. Where Q is the heat transfer rate, the amount of heat transferred per unit time, with a unit of watts. Then T infinity sub 1 is the temperature of the first fluid or the hot fluid. This is the bulk temperature of fluid 1 away from the wall, with a unit degrees Kelvin or degrees Celsius. Then T infinity sub 2, temperature of the second fluid or the cold fluid. This is the bulk temperature of fluid 2 away from the wall, with the same units with T infinity sub 1. And the next one is the H sub 1, convection heat transfer coefficient of fluid 1. It indicates how effectively heat is transferred from the hot fluid to the wall, with the units of watts per square meter Kelvin. And L is the thickness of the solid wall, with the units of meters. Then the K is the thermal conductivity of the wall material. It measures how well the material conducts heat, with the unit of watts per meter Kelvin. And the A is the heat transfer area. Take note that in convection, it is the surface area of the wall in contact with the fluid, while in conduction, it is the cross-sectional area through which heat flows. And for flat wall, these areas are the same, with the unit of square meter. And H sub 2, convection heat transfer coefficient of fluid 2. It indicates how effectively heat is transferred from the wall to the second fluid, and the units for this is watts per square meter Kelvin. And the R total, which is the total thermal resistance, it is the sum of all resistances to heat transfer. Also, take note of these two formulas, the Fourier's law for conduction and the Newton's law of cooling for convection. Now, let's move on to solving a sample problem. So the problem is a 1.4 meter long, 0.2 centimeter diameter electrical wire extends across a room that is maintained at 20 degrees Celsius. Heat is generated in the wire as a result of resistance heating, and the surface temperature of the wire is measured to be 240 degrees Celsius in a steady operation. Also, the voltage drop and electric current through the wire are measured to be 110 volts and 3 ampere respectively. Thus, regarding any heat transfer by radiation, determine the convection heat transfer coefficient for heat transfer between the outer surface of the wire and the air in the room. Here we have the given. For the length, we have 1.4 meter, and for the diameter, we have 0.2 centimeter, in which we need to convert the diameter from centimeters to meters. So the diameter is 0.002 meter. For the voltage, we have 110 volt, and for the current, we have 3 ampere. For the surface temperature, we have 240 degrees Celsius. For the constant room temperature, we have 20 degrees Celsius. And the unknown in this problem is the H, the convection heat transfer coefficient. Next, we calculate the heat transfer rate since the wire is in a steady state operation. The electrical energy generated is equal to heat transferred by convection, using the equation heat energy equals to voltage times current. Substituting the given values, we have 110 volts multiplied to 3 ampere. Since volts is joule per coulomb and ampere is coulomb per seconds, then we can cancel out the coulomb, leaving joule per second, which is the watts. Then therefore, the heat transfer rate is 330 watts. Now, we calculate the surface area of the wire. Since the wire is cylindrical, we use the lateral surface area formula. We have surface area equals to pi times diameter times the length. Then substituting the values, pi times 0.02 meters times 1.4 meters, and therefore the surface area is 0.00880 square meters. And finally, we apply the Newton's law of cooling. We have heat energy equals to convection heat transfer coefficient times the surface area times the surface temperature minus constant room temperature. Since we are solving for H, we rearrange the equation. So we have convection heat transfer coefficient equals to heat energy divided by the surface area times the surface temperature minus constant room temperature. Now, let's substitute all the known values. So we have 330 watts divided by 0.00880 square meter times 240 degrees Celsius minus 20 degrees Celsius. And after solving, we obtain 170.5 watts per square meter Celsius. And that would be all for this video. Thanks for watching.